Alright, this video is going to help us use a method called completing the square to solve quadratic equations. And I'll explain why completing the square is necessary in just a minute, but in order to complete the square, we first need to understand the perfect square pattern, probably a little bit better than we do already. You may remember the perfect square pattern a little bit from factoring, but remember that it applies both to factoring and also to FOILing. Remember, for factoring, it was the method where if you see a perfect square at the end of your function, such as a 16, and at the beginning, that you can try to take a shortcut to factoring by saying that x minus 4, if I see a 16, I know that there's probably a 4 in there, and x squared told me that x would be a great front term. And the reason I know that it works, remember, is that the first number times the second number times 2 will always give you the middle number. Or if you FOILed back together x minus 4 times x minus 4, remember that inside outside would be a negative 4x and another negative 4x, giving you together that negative 8x. Remember, that's what the perfect square pattern was going forwards. X plus 2 squared told us that we should take our first term squared, thus giving you x squared, your second term squared, giving you the 4, and the first times the second times 2, giving you that middle term. And the same thing goes if you have a number in front. 3x and negative 5, also going to be 3 becoming 9, 5 becoming 25, and 3 times 5 times 2 becoming that negative 30. And finally, if I see a 4 and I see a 9, I'm thinking that 2 and 3 will probably be great numbers. 2 times 3 times 2 giving us back 12, which tells me that the factored form is 2x plus 3 squared. So what do all four expressions have in common? They all have that perfect square pattern in common. Now, the complete the square pattern is actually saying we're going to have the first term and the second term, but we need to come up with what would that last term look like? What would the constant be? So when I think about a perfect square pattern, I think about the fact that I need to have x in order to become x squared. And I think that x times that blank number, times what I need to find, times 2. So 2 times x times, we'll call it a, need to give me that middle number. They need to come up to 2x. Well, if I divide out 2x here and I divide out 2x there, we'll quickly find out that a needs to be a 1. Therefore, my c right now, over here at the right, because this number squared will give me c, well, c equals 1 squared, or 1. Let's do that same idea for our middle term here. Again, I'm thinking about my perfect square pattern. X times some number times 2 needs to give me negative 6. Now you can set up some algebra if you want to, but if you think about it, what number doubled would give you negative 6? Well, negative 6 divided by 2 is negative 3. So negative 3 times x times 2 would give me my middle term. Well, if that's what my perfect square is going to look like, remember that my final term c, though, needs to be negative 3 squared. So c must have been 9. And finally, let's do that again one more time very quickly at the right, because this one gets a little trickier. X times what times 2 gives you 5x? Well, half of 5 would be 2.5, or 5 halves. And let's go ahead and keep that as a fraction. You can do the decimal if you'd like, but I kind of like working in fractions. Therefore, c equals, again, whatever that number was, squared to give me my constant term. Therefore, 5 halves squared, or c equals 25 fourths. And that would be completing the square. If I plug that in for c, we would have a perfect square pattern. Well, let's see how we can use that to solve an equation. The first thing you want to realize is, unlike factoring, I don't want all of my terms on one side. I'm not worried about being equal to 0. I actually like the fact that x squared and 4x are on their own over here at the left, and I'm going to leave that negative 1 on the right. Therefore, I can now try to complete the square. I know that I've got an x in the front, and I know that I'm going to have that perfect square, that quantity squared. The question is, what number again goes inside the parentheses. And remember that x times that number times 2 needs to give you 4x in the middle. So we better cut 4 in half, giving us 2. If that's going to be a 2 inside my parentheses, well, x squared is the front. X times 2 gave me 4x, and 2 squared would have been 4 up here. The only way we're going to factor correctly is if we have a plus 4 on the left side of our equation. However, to balance, remember that in completing the square, you can't just add 4 on the left side. That's basic equation work. You also have to add 4 on the right. So 4 plus -1 gives me 3. X squared plus 4x plus 4 factors to x plus 2 squared. -1 plus 4 is 3. And now we can solve our equation. Notice we just went from an equation that has an x squared and an x down to an equation that only has a single x within our look of our equation. Normally with x squared and x we would have needed to factor, but if you add 1 to the other side, I'd be willing to bet you that this equation was non-factorable. And you'll quickly see when I take the square root here, remember that the next thing I'm going to do is square root to start solving this, that I'm going to get x plus 2 equal to plus or minus, don't forget we took a square root, the square root of 3. Well, factoring never works very well, or at least it's a little tricky, when you're working with square roots. So you'll notice that for at least an exact answer here, if I subtract 2, it's going to be -2 plus or minus root 3, and we just found our irrational complex number answers. And notice there's no imaginary number, but we can still call this complex, but we do get 2 answers, -2 plus root 3 and -2 minus root 3 for our answers. Let's go ahead and do the same thing again for an example over here at the right. We'll go a little bit quicker this time though. So again, I like x squared and -16x all by themselves. I'm going to get rid of this -76 by subtracting it over to the right side. That way we have a nice blank spot to fill in for our completing the square. Now, half of -16 is going to be -8. Again, making our perfect square pattern, x squared, x times -8 times 2 gave us the middle, and -8 squared would be a positive 64. So let's add 64 on both sides, thus leaving us with -76 plus 64 is a -12. Well, let's go solve our equation then. Take the square root on both sides. We get x minus 8 equals plus or minus the square root of -12. Well, remember 12 is 4 and 3, breaking down into a 2 root 3, and a negative gives us I. Again, complex numbers also, when we were factoring, make that very hard to work with. If you again look for something that multiplies to 76 but adds to -16, my guess is you're going to come up blank. Thus our answers though, if we add 8 to the other side to finish, are 8 plus 2i root 3 and 8 minus 2i root 3, giving us 2 again complex answers. The last example for you just takes into account what do we do if we have a number in front. Now again, I want to set this up so I can complete the square easily. So the first thing I'm going to do is get rid of my 7, because I don't really care about having that constant there. I want to fill that in. The same thing goes for our 4. I don't like that 4 in front because that makes completing the square much harder. So I'm going to divide everything in here, including the 7, by 4. X squared plus 3x, I'm going to leave a little blank, therefore is equal to 7/4. Now let's go ahead and complete the square. Again, x plus half of 3, so I'm going to call that 3/2. Therefore, that number squared goes up top, 9/4. Let's add 9/4 to both sides. And 7/4 plus 9/4, realize equals 16/4, or 4. Therefore, we are equal to 4 down here. Go ahead and take your square root on both sides. So we're going to square root. X plus 3/2 equals plus or minus 2, which means x equals positive 2 minus plus a -3/2 and -2 minus 3/2. Well, 2, remember, is 4/2, negative 2 being negative 4 halves. And our two answers then are 4 halves minus 3 halves, or 1 half, and negative 4 halves minus 3 halves, or negative 7 halves, negative 3.5. And there are our two answers. Feel free to plug them back in, check them in the top equation. It's always a great idea, but that's how you're going to use completing the square to solve equations. On the next page, I just have a couple of more examples for you. Feel free to try them. I'm going to pause the video now and go ahead and put the answers in, and then show you one last example of where we can use completing the square. Alright, kind of walked you through it there, but hopefully you noticed as we went through, again, cutting that 8 in half, we found 4, squared it to find both sides, got 16, added it to negative 9, gave you 7. Took the square roots, subtracted over, and got our two clean answers there. Over here at the right, divided by 2 right away, get that x squared by itself, cut the 3 in half, made that 9/4. Add 9/4 to both sides. Remember, 2 plus 9/4 is 8/4 plus 9/4, or 17/4. Take the square root, took the square root on top and bottom. Square root of 17 really doesn't go anywhere, but now you've got a common denominator, so a good final answer written as one nice big fraction would be negative 3 plus or minus the square root of 17 over 2. Again, one last way we can use completing the square is to actually convert from standard form to vertex form on an equation. So a great idea here is to think about it as, let's try not to use the left side. Let's try not to even touch the y. Y equals is good. But if we think about completing the square, remember it only requires these two portions of our equation. So let's go ahead and write x squared plus 6x, leave a little blank, and I'm just going to leave 16 on the outside. I'm going to ignore it. Now when I go to complete the square, I need x plus something squared. Half of 6 would be 3. Remember, that means I'm going to put a 9 up here. Now instead of adding 9 also to the other side of my equation, I'm going to go ahead and say, well, hey, adding 9 to the left is as good as subtracting 9 on the right. Plus 9 minus 9 actually balances, and y equals 7 plus x plus 3 quantity squared actually gives me a nice vertex form equation, and I know that my vertex would be at negative 3, 7. Remembering that inside is opposite and outside is our vertical shift, so negative 3, 7 for a vertex. Let's go ahead and do the same thing over here on the right. Now, y equals, I'm going to leave the 2 outside the parentheses, but remember, because negative 16 is inside, I also need to divide out a 2 from there, so this makes a negative 8x, leaving 11 again on the outside. Go ahead and complete the square, so I'm going to make a perfect square model down here, cut my 8 in half, making that negative 4, adding 16 inside. Now notice that that 16 would also be multiplied by 2. So that's actually adding a 32, so let's balance by subtracting 32. And on the outside here, negative 32 plus 11 would be a negative 21. We're equal to y, and our final answer then, or vertex, would be at 4, negative 21. That's a great way to use completing the square, again, to convert from standard form of an equation to vertex form to possibly make it easier to graph. I hope those two examples weren't too fast for you. If they were, hey, feel free to rewatch. But good luck with completing the square, and have fun.